So again, welcome to Advanced Data Structure and Algorithm CS435 course. These lectures cover chapter 15, section 1 of our course textbook, which is a memory management. So here we say before a program can be executed, it must be again loaded from permanent storage such as a disk into a memory or a main memory, and must place within a process for it to be run. So again, a program must brought from a disk into memory and placed within a process for it to be run. Now, main memory and registers are the only storage CPU can access. So for example, a CPU cannot access a program or a file that is in a hard drive or is in a disk. It must be loaded into the main memory in order for a CPU to access it. So memory unit only sees the stream of addresses plus read requests or address plus data and write requests. Also, we know the design of a memory management portion of an operating system depends on the three fundamental areas of choice: whether or not to use virtual memory techniques, also the use of paging or segmentation, or both. Also the algorithms employed for various aspects of memory management. And we are going to cover some of the algorithms here. So again, a main memory can take many cycles, again, causing a store. And also caches sit between the main memory and the CPU registers. So the protection of memory required to ensure, again, a correct operation. Here we talk about the logical and the physical address space. So again, the concept of a logical address space that is bound to a separate physical address space is essential to a proper memory management. So logical address normally generated by the CPU and is also referred to as a virtual address. But the physical address is address seen by the memory unit. So a physical address would be the actual address of the memory. Normally, memory consists of cells, or we say a location, more or less like a cells, that each cell have a unique address. So again, the logical and physical addresses are the same in compile time and also the load time address binding schemes. And the logical or the virtual and the physical addresses differ during the execution time address binding scheme. So again, during the loading time, the logical and physical address are the same, but during the execution time, again, they are different. So a logical address space is the set of all the logical addresses that was generated by a program. But the physical address space is the set of a physical address generated also by a program. So a virtual memory is the separation of a user logical memory from, again, physical memory. So logical address space can therefore be much larger than the physical address space. And also only part of the program needs to be in memory for execution. Also, this allows address spaces to be shared by several processes, also allows for more efficient process creation. And also the memory management unit, which is MMU, must map the logical to physical addresses. So virtual memory can be implemented through demand paging and also demand segmentation. Again, in this course, we will not go details on the concepts here. The main reason why we are covering this section again, data structure again, when we create any type of data structure, it must be stored in a memory. So this topic normally, operating system, is where we go more details. Now with a demand paging, a page is brought into main memory only when a reference is made to a location on that page. Now, if other elements of a memory management policy are good, the following should happen, which is when a process is first started, there will be a flurry of page faults. As more and more pages are brought in, the principles of locality suggest that most future references will be to pages that have recently been brought in. So after a time, matters should settle down and the number of pages fault should drop to a very low level. And we may discuss this more when we went through the algorithms. Now with the pre-paging, pages other than one demanded by page fault are brought in. So pre-paging normally exploits the characteristics of most secondary memory devices, such as the disk, which have seek time and also rotational latency. Now, if the pages of a process are stored contiguously in secondary memory, then it is more efficient to bring in a number of contiguous pages at one time rather than bringing them in one at a time over an extended period. Now, in order to implement any data structure on an actual computer, again, we need to use computer memory. And this is the main reason why we are studying this chapter or this topic in our course. And again, this is the last chapter of our course textbook. So computer memory is organized into a sequence of words, each of which typically consists of 4, 8, or 16 bytes, depending on the computer. And again, these memory words are numbered from 0 to n-1. Okay, n is the size, where n is the number of memory words available to the computer. Also, the number associated with each memory word is known as, again, the memory address. So we have an example here of a memory, and we can see each box we call the cell have its own unique address. And normally, again, when we are writing a program, we don't have to be more concerned where, for example, if we declare variable or we create a data structure where it to be located, the operating system, again, randomly allocate the memory space for the process. So next is the object creation. Here we say with Python, all objects are stored in a pool of memory. And this is known as the memory heap or the Python heap. Now it's different from the heap data structure that we covered. So you have to say which should not be confused with the heap data structure. Now consider what happens when we execute a command such as widget, method or function assigned to W. What will happen is that a new instance of the class is created and stored somewhere within the memory heap. Again, this process is done by the operating system. Next, we talk about what is a free list. So a storage available in the memory heap is normally divided into blocks, which are, again, a contiguous array like chunks of memory that may be of a variable or it may be of a fixed size. Now the system must be implemented so that it can quickly allocate memory for new objects. And one of the popular methods is to keep contiguous or also available free memory in a linked list. And this linked list is called a free list. Now deciding how to allocate blocks of memory from a free list when a request is made is known as, again, memory management. And this is a very big topic in operating system. There are so many techniques we can use to manage our memory, or in fact, we have a memory management unit, again, in our operating system, one of the operating system functions. So several heuristics have been suggested for allocating memory from the heap. And the goal is to minimize fragmentation. And these are some of the few algorithms. And again, these algorithms are discussed in many operating system textbooks. So for example, we have the best fit algorithm. We also have the first fit algorithm, next fit algorithm, and also the worst fit algorithm fit. So let's go through one at a time. The best fit algorithm, normally we search the entire free list to find the hole whose size is closest to the amount of memory being requested. So if we find at least close to the amount of memory that we're requesting, and then we use that. And the goal, that's why it's called the best fit. But the next one, which is the first fit algorithm, it searches from the beginning of the free list for the first hole that is large enough. So if the first hole is bigger enough to accommodate our process, then it's assigned. The best fit will go through all the lists to find the enough fit for our process, whether the same size or the closest. Now with the next fit algorithm is similar, but in that it also searches for the free list for the first hole that is large enough, but it begins its search from where it left off previously. So that's why it's called the next fit, viewing the free list as a circularly linked list. And the last one is the worst fit algorithm. This searches for the free list to find the largest hole of a variable memory. And next we have what we call the garbage collection. Again, this is a process of detecting the store objects. For example, in Java programming, if an object is dereferences or it's no more reference to any item, again, Java garbage collection method will automatically remove it or clean it. But we also have, again, a garbage collection tool in an operating system. So the process of detecting the store object, deallocating the space devoted to those objects, and then returning the reclaimed space to free list is known as garbage collection. This again is done by the operating system. Now, in order for a program to access an object, it must have a direct or indirect reference to that object, such as object are live objects. Also, we refer to all the live objects with direct references, and that is a variable pointing to them as the root objects. And also an indirect reference is to a live object. It's a reference that occurs within the state of some other live object, such as a cell of a live array or a field of some live objects. We also have what we call the mark sweep algorithm. So with the mark sweep algorithm and the mark sweep garbage collection algorithm, we again associate a mark bit with each object that identify whether that object is live. Then when we determine at some point that that garbage collection is needed, we suspend all other activity and clear the mark bits of all the objects currently allocated in the memory heap. Now, when we then trace through the active namespaces, and we mark all the root objects as live, then we must then determine all the other live objects, the ones that are reachable from the root object. Now, to do this efficiently, we can perform, again, the concept of depth first search, which we cover again in our course textbook, chapter 14, on a directed graph that is defined by object references, other objects. Now, one thing we should know also is the concept of first in, first out policy. This normally would treat the page frames allocated to a process as also a circular buffer. And the pages are removed in a round robin style. So first in, again, the first out. So this is therefore one of the simplest page replacement policy to implement. And the logic behind this choice, other than simplicity, is that one is replacing the page that has been in memory the longest. Also, we have the memory hierarchies. We know from the lowest, which is the most expensive, to the largest. So normally, the most expensive memory, which is very small, is the registers. And the closer the memory is to the CPU, the more expensive it is. So registers are normally inside CPU. Then we have the caches, which are near to the CPU. Then we have the internal memory. We may have external memory, then the network storage. So here we say computers have a hierarchy of different kinds of memories, which vary in terms of their size and distance from the CPU. So as the distance is shorter to the CPU, the faster the CPU can access the data from the memory. So here we say the closest to the CPU are the internal registers. Access to search location is very fast, but there are relatively few search locations, again, very expensive also. The second level will be the cache memory, which is very near to the CPU. Then the third level will be the internal memory, which is also known the main memory or the core memory. Then we may have the hierarchy at the external memory, which usually consists of disk. So we can see the bigger goes up. So registers is the smallest, network storage is the biggest. The fastest, again, is the registers. Then the most towards will be the network storage. So we said about virtual memory. And previously, we said virtual memory always consists of providing an address space as large as the capacity of the external memory, and of transferring data in the secondary level into the primary level when they are addressed. So normally, virtual memory does not limit the programmer to a constraint of internal memory size. So the concept of bringing data into primary memory is called a cache, and it's motivated by temporary locality. We also use the term principles of locality. So by bringing data into primary memory, we are hoping that it will be accessed again soon, and we'll be able to respond quickly to all the requests for this data that come in the near future. Then we have the concept of page replacement strategy. So we know that when a new block is referenced and the space for blocks from external memory is full, we must evict an existing block. So there are several such page replacement strategy, including the first in, first out, or last in, first out, or randomly. We also have the concept of least recently used policy that replaces the page in memory that has not been referenced for a large, longest time. So here we have the random strategy. We choose a page at random to evict from the cache. So the overhead involved in implementing this policy is a big old one. So additional amount of work per page replacement. But still, this policy makes no attempt to take advantage of any temporal locality exhibited by the user browsing. So we can see the random policy, a new block comes in, we replace it with the old block chosen. Now with the first in, first out strategy, is quite simple to implement, as it is only require a queue to store references to the pages in the cache. So here we say the pages are NQ in queue object. So we basically insert the pages into a queue object when they are referenced and then are brought into the cache. Now, when a page needs to be evicted, the computer simply perform a dequeue operation. So first in, first out on the queue object to determine which page to evict. So we say this policy also require big big O1, additional work per page replacement. Moreover, it tries to take some advantage of temporal locality. So again, this policy is very simple. The whole concept of again is using a queue or circular queue concept. Now with the least recently used policy, it replaces the page in memory that has not been referenced for the longest time. So again, as we said earlier, by the principles of locality or temporal locality, this should be the page least likely to be referenced in the near future. And also, in fact, the least recently used policy does nearly as well as optimal policy. But the problem with this approach is the difficulty in implementation. So again, difficult implementation. One approach would be to tag each page with the time of its last reference. And this will have to be done at each memory reference. When each memory reference, both instruction and data. And also if the hardware will support such scheme, the overhead will be tremendous. Also, it has a big O1 overhead. So again, that will be the conclusion of our lectures on chapter 15-1. And we will go to the next lectures, which will be 15-2. So again, thank you.